in the top four equations, here's the behavior. So they took the equation, okay? Let's say this second one, all right? They took the equation, they plugged in some x's and got y's for you. They plugged in negative 1,000, they got negative 50,000. They plugged in negative 100, they got negative 5,000, and they marked those points for you. So if you were going to make a conjecture about the end behaviors of the graph, okay? Look as the numbers get really positive. They plugged in 0, 1, 10, 100, 1,000. Look what was happening to the outputs or the y values. Plugged in 0, got 0. Plugged in 1, got negative 1/2. Plugged in 10, got negative 50. 100 got negative 5,000. 1,000 got negative 50,000. Okay? Do you see the behavior of this graph when you're looking at those y values and how much they're jumping in between each input? Do you consider this shooting up towards infinity, shooting down towards negative infinity, or kind of evening out at one specific number? So when you look at, as I plug in these values, here's what's happening. What would you say is the behavior at this end of the graph? Brooke? Good. So going towards negative infinity, right? It doesn't seem to be leveling off. It just keeps getting greater and greater, like more and more negative. So we would say this one goes towards negative infinity. Okay? At the other end, okay, think about as you plug in more negative numbers, or in other words, as you go, x gets towards negative infinity, right? You go to the left of the graph. Plugged in 0, got 0. Plugged in negative 1, got negative 0.5. Negative 10, negative 50. Negative 100, negative 5,000. Negative 1,000, negative 50,000. What is the end behavior at the left side of this graph? Samantha? Good, the same thing, negative infinity. Okay, but do we see how I'm choosing that? I'm looking at the outputs and seeing what's happened. Let's look at a set of the middle four equations. Okay. Let's look at the third one in that set. If I was going to look at the end behavior here, okay, I see outputs of negative 14, 1.1, 0.3, negative 0.3324, negative 0.3333, okay? What's happening with the end behavior of this graph? Is it shooting up towards infinity, down towards negative infinity, or does it tend to kind of like settle on one specific number? Yeah, it's kind of settling, right? Negative 0.3324 and then negative 0.3333. Are those very far apart at all? No, but that was the jump we made. We had plugged in 100 here and then like 1,000 here, and that's the only difference that happened. A little teeny bit. Okay? So it tends to be settling at a number. Which number would you estimate that it's settling at? Yeah, 0.3333. So in fraction form, is it okay if I write it like that? So I'll just say like negative 1/3. Okay. We look at the other end, 1.1, negative 14, 1.8, negative 0.3254, negative 0.3339, negative 0.3334. What would you say is happening over here? Is it shooting up towards infinity, down towards negative infinity, or settling down towards one number? So remember, if it's shooting up towards infinity, you should see these things like drastically different, like 5, 100, 1,000, stuff like that. Show? Yeah, and this side, it happens to be staying at negative 1/3 as well. Now, the two examples we did both had the same end behaviors. The graphs won't always have that. We saw with our polynomial functions that doesn't have to be the case. Okay? So what I want to do is I want to give you guys some time in your groups to go back through what you looked at as the end behaviors, what you would determine now, and how that might affect your answers that you gave to the questions in number 2 about the first 4 equations, the second 4, and the third 4. Does everybody understand what they're working on? Okay, and again, if you need copies, there's a class set just of the chart and just of the questions that went with it on the side. Do not take them with you because I need them for further periods, okay? All right, so I'm going to set a timer, and you guys are going to be working on drawing. Okay. Let's talk about the first 4 equations. So let's talk about the end behavior that you guys established. And then let's talk about what that means for the answers to the questions. So what is the end behavior that you guys saw happening in this group of functions? So in the first 4 functions here, did you guys notice any patterns about the end behaviors? Yeah, Nicole. Okay, they were either positive or negative infinity. And sometimes it was the same at both ends, and sometimes it was different, right? So when we look at the questions we're asked about those first 4 equations, okay? In each of the first 4 equations, what is a true statement that you can make about the degree of the numerator compared to the degree of the denominator. So look at that first set of first four equations. What is a true statement that you can make about all of those when you look at the degree of the numerator compared to the degree of the denominator? Ashley?
When the degree of the numerator divided by the degree of the denominator was 2, it started at negative infinity.
Ooh, okay, that's pretty heavy. I don't know if it will always do that. No, but that's really good. I just didn't think anyone would go, look that into it in the patterns. I don't know if that's true for all the functions. In these four, it's obviously true. But that's not necessarily true for all of them. Brooke?
I said that they had a greater degree of x in the numerator than in the denominator.
Okay, so the degree of the numerator was greater than the degree of the denominator. So every function in that category was put there by the person that designed this because the degree of the numerator was greater than the degree of the denominator. Okay? Based on the limits that you found on the chart, can you make a conjecture about the end behavior of these types of functions? So what would you say about the end behavior of these functions? What did we just talk about? Nicole already told us what she found in the chart. So the end behavior either infinity or negative infinity. So knowing that and having seen that, the third part is, would we expect these types of functions to have horizontal asymptotes when we graph them? So would you expect a horizontal asymptote to show up on the graph of these functions? Michelle? Okay. No, because the graph, I'll say it continues to increase or decrease. Because I get what you mean by goes on forever. You mean up or down, but it's still going on. Because remember, the horizontal asymptote represents hey, at the ends, you're going to behave like this horizontal line. Well, if these are shooting up towards infinity or down towards negative infinity, we would not expect these type of functions to have this. So this is an important piece of information. When someone puts this crazy equation in front of us, if we see that the degree of the numerator is greater than the degree of the denominator, we're not going to expect to have a horizontal asymptote because we're going to expect to have end behaviors that kind of shoot up or down forever. Okay? They will follow some pattern, and we'll get into that a little bit later. All right. Second group of equations. Okay? What are some things you guys noticed as you filled in end behavior here? Okay, so first going to these questions here, when we compare the degree of the numerator to the degree of the denominator in that middle set of equations, the numerator and denominator have the same degree. So based on what we found in the chart, can we make a conjecture about end behavior? So someone tell me what you found for this first equation in the middle section. Michelle? Okay, so what did you get as the end behaviors here? 2? All right, for the second one, can someone tell me what they got? So when we look at these points, what we get. Yeah, Sean?
0.2.
Okay, so it looks like they're headed towards 0.2 on both sides. And in this last section, can somebody tell me what you got as the end behaviors for this function? Andrew? Okay. So we see one pattern that not only do they have some number that their end behavior tends to approach, but the number is the same at both ends of the graph, right? Okay. So based on the limits that we just saw in the chart, what's your conjecture about the end behavior? What would you say? We just talked about it. You basically said it, but summarize it up for us nicely. What's true about the end behavior of these functions that have the same numerator and denominator?
On both sides that they're almost the same.
Okay, so the end behavior is the same on both sides. All right, so would you guys expect these type of functions where the numerator and denominator have the same degree, would you expect them to have a horizontal asymptote? So if you were to go graph those functions that were in that portion of the chart, would you expect there to be a horizontal asymptote where the functions followed that number at the end? Yeah, okay. So, yes. Who could tell somebody why? If one of your friends from another class comes to you and says, I don't get why we said yes to this, what would you tell them? Why would you expect there to be a horizontal asymptote for these functions? Jordan?
Because they're going to the same number.
Sure. So the function approaches the same number on both ends. Okay. All right, so third set of equations that you looked at, we didn't fill in any of the end behavior here. Can somebody tell me the end behavior for the first equation in this last section of the handout? What did you get as the end behavior for this function? Ashley?
Negative 0.04 and 0.04.
Ooh, okay, close. Yeah, we're going to come back to it. You're right, but if we plug in another number, it will get here. Did anyone have anything different? No? Michelle? Yeah, it actually approaches 0 and 0. It's fair where you got what you got. It's not your fault for not. It looks like it goes to 0.04. Okay. The only thing that you would notice is that instead of this one being close to 0.04 and this one being close to 0.04, basically what's happening is this was 1 point something, right? And then it was like there were tenths. Then there were only like hundredths. So what would I expect the next one to be if I plugged in something? Maybe like 0.00 something, right? And so then that would kind of tell me that it's going towards 0. All right, what about this one? 0, right? Same thing's happening, right? So it's like 0.1 and then 0.0 something and then 0.002 and then I would expect 0.00 something and the same pattern I'm seeing over here. Okay? All right, what about the next one? 0. And the same pattern is happening, right? What's happening is the decimal's moving over and over and over. So eventually what's going to happen as we plug in larger and larger and larger numbers is we're going to have 0.000000 something, right? Which is what we talked about with our reciprocal function, okay, which is how we knew that it approached 0. Okay? So this is what we get for the end behaviors here. Okay? So looking at the questions that go with this, okay? So first of all, what was the comparison between the degree in the numerator and denominator with this group of functions? Yeah, Alvin. Good, okay. So the degree of the denominator was greater than the degree of the numerator. So based on what we just looked at in the chart with the end behavior, what would you tell someone? Oh, when I look at a function where the degree of the denominator is greater than the numerator, here's what I expect from the end behavior. What did we say? What did we see show up? We just filled it in together. What did we see show up? Look closely. Okay, they're all 0 here on this end and on that end. Okay, so based on the limits we found in the chart, our conjecture about end behavior would be that the function's always approaching 0 at both ends. Okay. All right, so somebody tell me, would you expect if I lay in front of you an equation where the degree of the denominator is bigger than the degree of the numerator, would you expect to be marking and labeling a horizontal asymptote on your graph of this function? Yeah. Okay, so I see some people shaking their heads, right? Yes. Okay. Okay. And I think it comes back to what Jordan said last time, because it's leveling off at the same place on both ends, right? I would basically say because of this, right? Right. So the differentiating factor between the different equations is the degree of the numerator versus the denominator, right? And it kind of falls into three categories, and we saw these three different things happen. So we want to make some big conclusions, okay? So go ahead and in your group, I want you to fill out this chart as much as you can, and we'll come back together. So there's three different situations, just like there was. The degree of the numerator is blank. The degree of the denominator, the degree of the numerator is blank. The degree of the denominator, the degree of the numerator is blank degree. So one is going to be smaller, one is bigger, one is equal to, right? Write an example of an equation that would be that type of equation. You can make up your own. You can use one from the chart. Is there a horizontal asymptote? You should be able to dig into what we just asked to determine that. And now a new question. How do you think you would find that horizontal asymptote? Okay, so a couple minutes for you guys. All right, so bring it back together and let's talk specifically about how to find this. Maybe some of you guys made some observations, maybe you didn't. I'm just going to do it in order of the chart. So when the degree of the numerator, and if you did yours in a different order, that's fine, don't freak out. Just whatever I fill in the greater than, make sure you're filling it in your chart in the greater than, okay? So when the degree of the numerator is greater than the degree of the denominator, when it's equal to the degree of the denominator, and then when it's less than the degree of the denominator. That's kind of the order our chart went in, so that's why I did that. So example, you could have made your own or filled one out from the chart, okay? So when the degree of the numerator was bigger than that of the denominator, was there a horizontal asymptote? No. Okay. So how is it going to be found? It's not, okay? So instead what you're going to do is you're going to find what we call an oblique asymptote. And you'll see in video notes tonight how to do that. And basically the way you're going to do that is you're going to use division. Okay. So an oblique asymptote means it's not something that's horizontal. So maybe you have a function. I'm just going to use this space to draw for a minute, but you don't have to draw the same thing. Maybe you have a function that goes like this, and then does this, and goes like this or something. Maybe its end behavior, it's behaving just like x squared. It just did weird stuff in the middle, right? So it could have an end behavior of x squared, okay? That would be oblique because it's not horizontal, okay? Or maybe a function does this. I know, super weird, okay? But you'll see some like this today. Well, the end behavior of this, look, if you ignore all the stuff happening in the middle that's all crazy, the ends kind of just look like a line, right? So in that case, the oblique asymptote, you're going to say, at the end it behaves like this line, like y equals mx plus b, maybe a slope of 3, maybe a slope of 2, okay? And you'll get that by using division, okay? So you'll still have something to guide your end behavior, it just won't be horizontal. All right. Middle section. The degree of the numerator was equal to the degree of the denominator. Did we decide there would be a horizontal asymptote? Yes. Okay. But they were all different, right? They evened out to the same number, but it was different depending on the function. Let's look and see if we can find a commonality between what the function looked like and what number it was evening out to. Okay. So here's what this function looks like, right? And the horizontal asymptote for this function would be y equals 2. Okay, so I'm trying to think in my head, is there any relationship between what's going on here and 2? Here's what this function looks like, okay? Its horizontal asymptote would be y equals 0.2. Just for reference, 0.2 is also the same thing as 1/5. Okay? Here's this function, okay? Here's what it looks like. Its horizontal asymptote would be y equals -1/3. Here's this function and what it looks like, and its horizontal asymptote would be y equals 4. Those numbers are related to the equation. Does anybody see a pattern that they think they've caught on to? Jordan? Okay, good. So it's the ratio between the lead coefficients of the numerator and denominator. So you know how we said the numerator here, okay, we would say it's degree 1, right? And the denominator's degree 1. Take that highest degree term and look at the coefficients. 12 over 6. 12 divided by 6 is 2. Okay? Here, lead coefficients, doesn't have one, so it's 1. 1 over 5 is 0.2. Okay, here it's not written in order. You don't take 14 over 9 because 14 wouldn't be the lead coefficient. It would be negative 3 over 9. And negative 3 over 9 is the same thing as negative 1/3. Okay, and here, 8 over 2. 8 divided by 2 would be 4. Okay, so the function can tell you, without doing a lot of work, exactly what the horizontal asymptote is. Okay, so you need to use the lead coefficients. Okay, if you need to make some further notes about that, make them for yourself. Basically, it's going to look something like something from the first one, something from the second one. Okay, but those numbers are specifically the lead coefficients of the numerator and denominator. Okay. All right, third set of equations had everything set up where the degree of the numerator was less than the degree of the denominator. Did we say there would be a horizontal asymptote for those? Yes. Okay. Again, because they evened out to the same number. But in this section, it was like the nicest section, so to speak, right? They didn't just even out to some number. They all evened out to what number? 0. So it didn't matter what the coefficients were, what the equation looked like. If the degree of the numerator was less than that of the denominator, then the horizontal asymptote was sitting at y equals 0. Okay? Is this all right with everybody? All right, so when you watch tonight's notes, so this is a long section, obviously. We're not going to get to any examples today. We're just kind of learning all the parts, right? And then tonight's notes will be 5 graphing examples. And even though there's 5 of them, they're a little bit longer than what you would expect because there is a lot of parts to graphing these, okay? For every equation that's laid in front of you, you want to find all of these things, okay? So let's talk a little bit about each of these so that when you see it in the notes tonight, you have this in front of you reminding you of, oh, yeah, that's how we find that, that's why, okay? So first thing, vertical asymptotes. When do vertical asymptotes show up on the graph? What do they represent? We've talked about them before. A vertical asymptote is on the graph to represent what, Ben? Where the graph is undefined. Now, even though these functions don't look like your other ones were all these nice little reciprocal functions, right? When did the function end up undefined? When there's a fraction involved. What specifically were we looking for? Sean?
Denominator equals 0.
Good. Okay. Now, even though these functions are all different, did they all have a denominator? All the functions that you looked at in that chart today? Right? Okay. So, where is the fraction undefined when the denominator is set equal to 0? So how are you going to find your vertical asymptotes? You're going to set the denominator equal to 0 and solve for x. And then you're going to have x equals whatever this is, maybe 1, maybe 2, maybe 3, I don't know. Right? Depends on the function that's underneath there in the denominator. Okay? These are called non-removable discontinuities. Okay. Discontinuity is in their name because the graph doesn't cross them, right? So they make it to where you have to pick up your pencil to finish drawing the graph. So they are making the graph discontinuous. Why they're called non-removable, we'll see when we talk about holes in a minute, okay? If there's a non-removable one, there must be a removable one, right? What that is. All right. Horizontal asymptotes or the end behavior. We just had this huge discussion about end behavior and horizontal asymptotes. What do you think you need to look at when someone puts the function in front of you to determine if there is a horizontal asymptote and what it is? Good. Okay. So you need to compare the degree of the numerator and the denominator. And then you have to use the chart that we just came up with, right? Sometimes it'll be 0, sometimes it'll be the coefficients, or sometimes there won't be one, okay? When there wasn't a horizontal asymptote, what did we say would exist? An oblique asymptote. So both of these do the same thing. They both describe end behavior. So is your equation ever going to have a horizontal asymptote and an oblique asymptote? No, because it's either going to end like this or it's going to end doing something else. It can't do them both, okay? So it's either going to have a horizontal asymptote or an oblique asymptote because they're both the same type of thing describing end behavior, okay? So you get this when there is no horizontal asymptote, okay? And you get it by using division to get an equation. Because all of your rational functions, there's something over something, right? We say over, but what does that fraction bar really mean? Divided by. So you're literally going to take it and divide it out like we did in the last unit. Like I'm going to take the numerator, I'm going to divide it by the denominator, I'm going to get some new function. That new function is what my oblique asymptote is. Maybe it's a line and I draw a little dashed thing there. Maybe it's a parabola, I draw that in all dashed so it can follow the ends of that. Okay? Something like that. All right, holes. Okay? So sometimes your graph are going to have holes in them. Seems really super weird, okay? They call these removable discontinuities, and here's why. Let's say that someone put this equation in front of you. Actually, okay? The first thing you want to do is you want to factor it. So you're going to see in the videos today, every time I have an equation, the first thing I'm going to do is write it in its factored form. So if you still can't factor after we did quadratics, after we did polynomials, after we did the beginning of this unit, which required you to factor and cancel, you're going to need to factor to graph these as well. It's an essential skill, okay? Can I simplify this function? Yeah, right? Oh, and it becomes a function that I love so much now. Okay, I maybe hated that one in Algebra 1, but come Algebra 2, this is like a beautiful little function, right? What is the graph of this going to be? A line. It's just the line, x plus 2. That's all this is. But in the original function, couldn't you plug in -1? If you plug -1 into the original function, what happens? You get 0 over 0. Mathematically, do we have a value for that? No. So even though this simplifies to just be this, can you plug -1 into our new function? Yeah, 2 plus -1 is 1. So here's the problem. Your new function, which is supposed to be the same as your old function, right, lets you plug in -1 and get a point on the graph, but our old function says, So essentially what you're going to do is you're going to graph this line, so it's going to be on your graph something like this, and you're going to go to the point that -1 would have made. See, when we plug in -1, we get 1, right? So you're going to go to the point -1, 1, and you're going to erase it and put a hole. Because it's like, it is this line, but not with this one point, because that doesn't work in the original one. Okay? Super weird. So why they call them removable discontinuities? This would have been a vertical asymptote if it didn't cancel out, right? Because the denominator would have been equal to 0 at x equals -1. It would have been undefined. But when it cancels out, it now has been removed, okay? So it becomes a hole instead of a vertical asymptote, okay? So in order to find these, you're going to factor and look for factors that cancel. Okay? And this is just an overview. You're going to see some hardcore examples step by step in the videos. X and Y intercepts. How do you find an X-intercept for any function? Plug in 0. If you have a fraction, just a helpful hint here, if I plug in 0 for y, I don't know, and I have this, which part of this fraction needs to be equal to 0 for the answer to be 0? Ashley? Good, the numerator. If the denominator is 0, what's going to happen? It's undefined. That's a whole different thing. And if you go to solve this, the first thing you're going to do is multiply both sides by x minus 1. And what's going to happen when you multiply this side by x minus 1? So what do you think is kind of a shortcut to finding x-intercepts every time your equation is in fraction form like this? Which part just really has to be set equal to 0? The numerator, right? It's really going to be determined by the numerator. So if that helps you, you can use that. All right, and then how do we find y-intercepts? Good. Okay. So plug in 0 for x, solve for y. And I'm not changing your x-intercepts, okay? I don't like when people leave and they're like, oh, Ms. Dahl told us x-intercepts now a new thing. It's not. You're still doing the same thing. You're still plugging in 0 for y and solving for x. But when you do that enough times, you're going to see this pattern show up, and you're going to be like, forget doing all these steps previous to it. I'm just going to do that. Okay?